Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh, Syallom, Namo Budaya, Salam Kebajikan. In this video, I will explore about modern alloy production. First, let me introduce myself. My name is Elkana Silitonga, with name 230553107 from Metalurgi Class C. This course is taught by Prof. Tjokorda Gde Tirta Nindhia STMT. My reference, the book Metalurgi or the Non-Metalurgist, Seccond Edition, edited by Arthur C. Riordan. Contents: 1. Effect of alloy on solidification. 2. Solidification structure. 3. Melting furnace. 4. Molten metal process. 5. Primary production casting. 6. Foundry casting. 7. Non-ferrous casting alloys. 8. Powder metallurgy. Modern alloy production. The manufacture of modern alloys is accomplished using a wide variety of melting, casting, and fabrication techniques. Practically all of the commercially available alloys produced today are manufactured using melting and solidification techniques that have been refined over time to produce an acceptable level of quality in cost-effective manner. The alloy production methods may consist of traditional air melting practice, vacuum melting methods, or powder production techniques. In the majority of melting operation, after the liquid metal is produced, it is cast into molds. At this point, it becomes either an ingot or a casting upon solidification. Use of the then ingot is reserved for the furnace output mold form that is intended for shaping into a marketable material for subsequent mechanical reduction operations. Alloys processed in this manner are known as raw products. Wonders that are formed into acceptable shapes by casting only are called cast products. Cast materials typically require less labor and fewer processing steps to produce than their work counterparts, but they also process more heterogeneous microstructures that have a higher probability of containing imperfections, such as porosity, for example, that might adversely affect properties and performance. 1. Effect of alloy on solidifications. The solidification of alloys is a complex process, and it is most easily understood by examining how the solidification characteristics of alloys differ from those of pure metals. The solidification of pure metals: when a pure metal begins to melt, the solid liquid mixture stays in the melting point temperature until the solid has completely melted. The amount of thermal energy needed to complete the transformation from solid to liquid is defined by latent heat of fission of a material. For example, pure aluminum begins to melt at a temperature of 660 Celsius and has a latent heat of fission of 398 kJ or kilogram. If a pure metal is melted and allowed to solidify in the melting crucible, and thermocouple pairs in the metal during solidification, or there is a cooling curve like that shown in the figure below. During the early stages of solidification, the temperature might fall slightly below the melting point or impact of the metal. This phenomenon is referred to as supercooling or undercooling. A slightly different cooling curve can be observed when the molten metal includes some minute solid impurities, such as particle of dust or small trace of the refractory brick used to line the interior of a melt furnace. In the picture below, the cooling or supercooling of liquids is common phenomenon, while the superheating of solid is not. The liquid may perform much more readily when a metal meets the solid nuclei in a liquid course. Solidification of alloys. The solidification of alloys is more complex than of pure metals because the different elements in alloys process different melting temperatures. Pure metals freeze and melt at specific temperature. Alloys that freeze and melt over at temperature range. In fact, alloys with near-acoustic composition are the dominant alloys used by foundries in the self-casting of components. For example, cast irons and alloys that use the iron carbon and aluminum silicon alloys are another example of a major family of self-casting alloys with a eutectic point. The aluminum silicon eutectic is located at approximately 12.6 with facets SE and 577 Celsius on the binary phase diagram in the picture below. Alloys that process relatively wide freezing range can be prone to void formation, porosity during casting, while alloy composition near eutectic melting point, where the freezing range is much lower, can have clear effects in casting specific shapes or geometries under certain conditions. This is particularly important consideration in aluminum silicon alloys, which have been used for decades in the automotive industry for casting engineering blocks in the picture above. Solidification structure. During the solid liquid interface during solidification normally exhibits one of the types of crystal growth in the liquid, planar, cellular, or dendritic growth, as shown in the figure above. The type of growth is controlled by the manner in which heat is removed from the system, because the temperature gradient is linear and uniformly perpendicular to the interface. A smooth interface is maintained and the growth is planar into the liquid in the picture above A, when its temperature information and the temperature decrease a heat of the solid liquid interface, then either cellular or dendritic growth will occur in the picture above B and C. Thermal supercooling. Cellular growth is illustrated in the picture above. Occurs when the advancing planar solid liquid interface becomes unstable and small sphere appears on the interface that then grows into a cellular type structure. The planar surface becomes unstable because any part of the interface that grows heat of the remainder enters a ligand, and in the liquid the heat is at lower temperature. At still higher undercurrent and higher core voltage, the curls grow into rapid advancing projection, sometimes of complex geometry. Dendrites are small crystalline nether shapes, like pine stars in the figure below. So named after the Greek word dendros, forte. Constitutional supercooling. While dendrites can form to limits extent if pure metals due to temperature inversion, they are more frequent in alloys because of the external undercooling due to conventional supercooling. The liquid is said to be liquidly conventional supercooling, that is repeatedly undercooled because of a change in the composition of chemical makeup the liquid. Solidification zones. A metal cast into a mold can have up to 3 distinct zones of types of granules. Axial zones, a zone containing corner grains and a center extracted grain zones in the figure below. However, it's all may not that all three zones do not always occur. For example, the solidification structure of few metals exhibit axial zones and columnar zone, but may not contain a center extracted zone. Silitonga's nucleus force occurs of the interior of the mold because the mold is colder than metal. As a result of the temperature difference, the nucleation thread is internally high and the reference grain size is typically small. Its nucleation even produces an individual crystal of grain that goes decline in direction slowly perpendicular to the mold, until it impingement of other grains in figure below. Columnar zone. Inside of the seal zone, there are a series of columnar or column shapes, grains that are rotated almost parallel of the heat flow in the direction. The final columnar structure results from parallel growth of different columns of dendrites and the grosser lateral or tightening between them. However, if casting condition change, some of the floating dendrites can be detected by the convective motion of the map. This determining of the formation of an acoustic structure in the middle of the ingot. The figure below. Center consist zones. A triangle at the center of some alloys consists of smaller grains that are randomly oriented and alloy acid mining crystal are similar in like, braided, and white. Massive facing. Alloys with alloy facing lines is may difference in solids and crisis temperatures. Solid with mostly corner solid, white alloys with white facing lines with Tugas long facing grains alloys. Solids with mostly exposed grain structure and normal columns. This local increment surprise growth of the first crystal, but cross condition favorable for the nucleation of a second set of crystals just beyond the first in the figure below. A and B. The process is repeated as many times as necessary in the figure below C and D. The grains these tend to be exquisite if crystal growth is sufficiently suppressed. The drinker growth also can be suppressed. Non-dendritic solidification for semicell process. Semicell alloys production with an non-dendritic microstructure in the figure below. With important emphasis for Bab 7. Some alloys polycyclic and can be injected into mold cavity. Much like the injection molding of plastics, the behavior arises from the global microstructure of the semicell molds. During the early stage of solidification, the microstructure of cast alloys can be altered from an indirect structure toward the set of spherical morphology in the figure below. First, consistent currents of mechanical action increase sharp and terminals in the circuit, which promotes the solidification of the bulbous simulus structure. Melting furnace. When furnace technologies are available for melting metals in smelting, for example, pig iron is produced in blast furnace from iron ore, limestone, and cube in the figure above. This choice of melting furnace depends of the specific alloy, the casting operation, and the required quantities of to be produced. Furnace vary in size with output ranging from a few pounds to several hundred tons. For low temperature melting points alloys, such as zinc or lead, for example, temperatures may only need to reach as high as 400 Celsius. In steelmaking operation and iron furnace, the electric arc furnace is commonly used. However, cupola furnaces are used where large torrents are required for iron melting. Melting is in cupola furnace dates back several centuries to the old cast types, units that were operated with hand pumped wheels. Another important type of iconic furnace is the reverberated furnace. Reverberated furnace have a special head for melting metal, which is heated by a furnace mount in the roof or in the sole of the furnace. Electric arc furnace. Of the furnace most commonly used to melt steel alloys in the electric furnace or EF. A typical EF is a regularly round vessel with equal shapes that is covered with a rectangle spherical roof. Alternating current furnaces are powered for further steel casting in the figure below. And typically F3 large general shaft electrodes that have head-treated coupling on one end. Induction furnace. Induction furnaces have become a wide use means for melting ferrous alloys and increasing non-ferrous alloys as well. The key to the already absence of induction has been the excellent metallurgy control that can be exerted coupled with Relative in Alloy Production compared to cupola furnace in making and good amount efficiently compared to EF melting. When the source is located at the lines of magnetic flux also cause metal movement, which includes electromagnetic state in the figure below. Vacuum introduction melting. Melting under vacuum is an introduction heat crucible is tight and the step progress in the production of liquid metal. It has origins in the middle of the 19th century, but actual technical breakthroughs occurred in the second half of 20th century. Vacuum innovation melting can be used to effects in many applications, particularly if the case of the complex alloys operate in aerospace engineering. Crucible furnace. Crucible furnaces have historically been the most common type of furnace used and records dating back to the dawn of the metals industry some 6,000 years ago indicate their use. The crucible furnace of antiquity were in form of wire, clay pots, and gave metals the ability and crucible container that could be used to prepare molten material in the mold. At the mold's basic level of form and function, modern crucible furnaces are similar in concept to their early prototypes. Modern methods of construction in the figure below have improved to their thermal efficiency and several life considerably. Remelting. There are two commonly used remelting processes for metal removing circular melting, ESL, and vacuum remelting, VAR. The ESL and VAR methods are very different from each other, and these differences have implications regarding the nature of the effects that can be created by the melting process itself. The VAR process is carried on in vacuum, while the ESL process typically occurs under amorphous condition. Ortho ESL and under vacuum vac ESL or other process is an version of the standard ESL process. The VAR process was the first commercial remelting process used for separately, and the difference can vary considerably in the size and simplicity. An example of Presentasi 30 tons furnace is illustrated in the figure below. Other furnace. Several other types of furnace have been developed for special applications. For example, screw melting is technique that is used when melting highly reactive metals. This is titanium and zirconium. The world others like the walls of incredible layer with standard recovery materials. Molten production casting. Molten metals are processed and handled in various ways depending on the alloy and molten practice that are used. Molting is a basic way of combining the elements of the purpose of alloy, and the overall chemical condition of the molten alloys must be careful controlled by and processed before casting can take place. Friction of molten metal is often the first step in obtaining a clear melt. Friction is the term commonly used in foundries and melting departments. The reverse the molten metal remains from the addition of reactive chemical compounds in or inert gas. The various functions of metal friction is either single inclination include inclusion imports of dissolved gas from the melt, preventing excessive formation of solid inclusion, preventing an or non-forming oxide build and furnace walls, injecting or static alloys. The function of flux is to render to high melting recovery oxide import is feasible and separable from the molten metal. The fluid and medium weight, which the impurity elements are combustible, combined in preface to the metal. The basic types of NIM flux are copper flux, Dawson flux, metallic flux, volcanic flux, fluxing of under non-ferrous flux. It includes fluxing of magnesium alloys, fluxing of copper alloys, fluxing of zinc alloys. Primary production casting. Foundries various methods to cast parts with complex shapes and interior surface mold or match in variety of alloys so that the molten fuel into the mold cavity result in parts with the shape and dimension of the finished form. Foundries also require the use of ingots in the figure below. It can be limited to sometimes called big ingots. The private fixation complete combustion. Static ingot casting. Several ingot casting processes have been designed and developed for downstream manufacturing process. The most common is static ingot casting, where molten metal is processed into vertical orbit unit mold. A number of inseparable events may take place during this certification of cast ingots. Cyanide and gas cavities are some of the most characteristic feature and common defects in any cast metals. Other defects the may is ingot during casting and certification. The common result in cracking during forming, rolling, or instructing includes 1. Metal inverts, 2. Non-metallic inverts, 3. Slide doors and flexion inclusion for interior microstructure, 5. Stigration, 6. Surface and 7. Internal column cracks. In addition to this, session issues the static casting process has inherent shortcomings. It is batch process, which makes it less than ideal in terms of production efficiency. Continuous casting process. Continuous casting may be defined as the continuous solidification and wet roll of ready from and abandoned shaping molds. Today, continuous casting is common production of fasteners, copper alloys, and aluminum alloys. The quality of continually cast metal can, in certain respects, be superior to the of stability excellent. In this super time, the continuous caster can be shut down and section of the ingot crop and removed from the holding pit. Then the process can be restarted. This is known as selection casting. In another process, the product is made in figure below. That is emerged horizontal from the casting segment. From work aluminum alloys, the direct self-DC simultaneous casting process are one of its two. Variation is the third method in use today for production and build products. This process developed in 1933 by with influence pouring aluminum into a alloy with a coated mold in the cross-sectional surface. The ingot or section desert in figure below. The DC casting process can produce of fine-grained ingots with a minimum amount of segregation at rapidly high production rates. The progress can be vertical or horizontal. The figure below. Foundry casting. Foundries use various methods to decast parts with complex shapes and increase surface amount in a variety of ways, so that the molten metal poured into the mold cavity result in part with the shape and dimension of the finished form. Self-casting methods can be divided into the broad categories: casting with expanded molds, casting with reusable, casting with reusable permanent molds with high pressures. Example mold methods are classified further as either expandable molds with permanent, expandable molds with expandable patterns. The permanent pattern is negative mirror image of the part to be cast, and the patterns are used to form activity for the cup or top and the bottom section of the mold in figure below. After the patterns are removed, the cup and the section are sealed together for casting. The common methods use expandable patterns made of or wax and alcohol plus from and investment plus wax. Casting is subsequently unlike permanent patterns for molds. Expandable patterns are positive replica of the part in figure below. In lots from casting, for example, of composite is pellets and wax. There are two distinct processes for making investment casting molds: the solid investment solid mold process and the ceramic cell process. The ceramic cell process in the figure below A has become the permanent technique for generic complication is displacing the solid investment process in figure B. Permanent mold casting is particularly stable for the high volume production of casting with fairly uniform wall thickness and limited intercross or incurred internal coring. Metals that can be cast in permanent molds include the aluminum, magnesium, zinc, and copper alloys, and heavily ground iron. The vast majority of permanent mold casting are made of aluminum alloys in the figure below. Decasting. Decasting is generally limited to metals with low melting points. However, high-speed casting (HPDC) is one of the fast methods for net shapes manufacturing of parts from diverse alloys. Aluminum is the most commonly used alloys for decasting, followed by zinc, magnesium, copper, tin, and lead parts produced by the casting process of some. In the figure below, the primary categories of the conventional decasting process and the hot chamber process and the cold chamber process. The various casting alloys. In terms of tonic cast iron is the most commonly found alloys, consisting of approximately 3/4 of the worldwide production of casting of non-ferrous alloys and tonic bases is dominated by aluminum in terms of both annual and continuous process in primary production and then tonic by foundry or shape casting. Aluminum casting alloys. Aluminum casting alloys are the most versatile of common foundry alloys and generally have the highest cost stability ratings, and casting metals aluminum alloys have these favorable characteristics: good fluidity for killing the section low reduced temperatures, relative reduced recovery from many of metals, rapid heat transfer from the molten aluminum to the mold, proving sharp and casting characteristic. Many aluminum alloys are relatively free from hot shock breaking and tearing chemistability. Aluminum paper alloys contains 4 to 5% CuN are heat treatable and creates good high strength and decrease, especially if prepared from ingot containing less than 0.15% Fe. Aluminum cover silicon alloys. The most widely used aluminum casting alloys are the content silicon and copper. Aluminum magnesium casting alloys are essentially based binary alloys with moderate to high strength and toughness properties. Aluminum zinc magnesium alloys natural X exceeding full strength by 20 to 30 days and room temperatures after casting. Aluminum tin alloys that contains approximately 6% SN and small amounts of copper and nickel for tightening are used for cast bearings because of the excellent quickly imported by tin. Copper casting alloys. Copper casting alloys are available in some continuous centrifugal permanent mold and some decasting. Copper casting alloys are used for the cornice sections and their high thermal and electrical conductivity. Magnesium casting alloys. Magnesium casting alloys of all types have found use in many commercial applications, especially where their brightness and electric are major events such as far scan cell bodies, computer components, camera bodies, and curtain portable tools and equipment. To see casting alloys, the casting is the process most often used for shaping zinc alloys. Water metallurgy. One of the more recurrent metallurgy developments in the manufacture of modern alloys is the development of water metallurgy or PM process. Metal products can be produced using a wide variety of mechanical methods as well as base chemical and electrochemical methods. Aluminum is the dominant metal of reduction metal products from aluminum, brass, iron, wall, alloy steels, stainless steels, tool steels, super alloys, titanium alloys, and many other important industry alloys. Atomization is simply the breakup of a liquid into fine droplets. The general types of atomization process involves a number of industrial and basic methods. Industrial methods include with atomization, where liquid metals is broken on drops by emitting of high pressure jets of gas, whether or air, in the figure below A and B. Central atomization, where a liquid stream is dispersed into the droplets by the central force of water in this cup or electrode, in the figure below C. Vacuum or scalpel gas atomization, where molten metal is supercharged with gas that gives atomization of the metal in vacuum, in the figure below D. Ultrasonic atomization, where a liquid metal film is activated by ultrasonic fabrication, in the figure below A. Water gas, centrifugal, ultrasonic, and solid gas atomization are also used in commercial production, but to fluid atomization methods with gas include air or water account for more than 95% of atomization capacity worldwide. Water atomization is termed of today. Water atomization is now the primary mode of atomization for metal, especially for metal powders. In general, water atomization is less expensive than other methods of atomization because of the low cost of the medium of water, lower energy of use for precision compared to gas air atomization methods, and the very high productivity that can be achieved up to 30 tons or high approximately 500 kilogram or mean whether atomization by generally produces interglacial powders of relatively high oxygen content as schematic flow sheet of the better atomization process installed in the figure below. Gas atomization process generally produce powder particles that differ from the produced by water atomization process in terms of the geometry and surface chemistry. Gas atomization differs from the water atomization in several respects, rather than by limited by process of the medium. In water atomization is found that the gas to metal material in the dominant factor in controlling powder particle size, with median particle size being related inversely to the square root of the gas to metal ratio. Gas atomizing units also come in with much wider range of design than water automation and classified as either confined or free wall. As a comparison in the figure below. Okay, that's all the material I can convey. Thank you. Santiong. Waalaikumsalam warahmatullahi wabarakatuh. Syallom, Namo Budaya, salam kebajikan.